background of my mic. Okay, so welcome everybody, and welcome Mike, who'll be talking to us today on non-reciprocal acoustics. So I won't do a very long introduction because we've already had a very nice bio emailed out. So all I'll say is that we have our speaker, which is Dr. Michael Haberman. He is an assistant professor at the Walker Department of Mechanical Engineering in the University of Texas at Austin. I'm sure many of you will be aware of the type of research that Mike has been involved in the past. Lots of the students that may be on this call will already recognize Mike's work, because I make everybody read the Physics Today article on acoustic metamaterials as the first primer and background to sort of frame what we're talking about, particularly in our department. You know, in there lies lots of work right from the theoretical all the way to the practical and proper acoustics, real demonstrations of devices. So, you know, it promises to be a very interesting talk, and I'll say no more. What we usually do is we put questions in the chat, and either myself or Kellen will address those to Mike at the end. So over to you, Mike. And I should say thank you very much ahead of time, because it's actually, I should have said, you're in America right now giving this talk, so you're up bright and early. We've already had a discussion about how the sun is usually shining through the window, illuminating Mike much better than he normally is. So thank you very much for being up so early.
Yeah. All right. Okay. Thank you. Yeah. So usually I told Tim and Kellen that usually the sun is shining through my windows, which you can't see, is just on the opposite side here. So I'm a little dark in the shadows. I apologize, but maybe the sun will come up in the interim here. So in any case, I appreciate the invitation. Thank you all for coming out and listening on a late in July. So I'm going to, without any further delay, I'm going to talk about non-reciprocal acoustics, and specifically I'm going to talk both kind of on a very, on a more conceptual level, some of the ideas, and kind of disambiguate or kind of demystify a few things. Ideally, some of you may be familiar with these concepts, but then also talk about sound diffusion. So how basically we can take some of these more general, and let's just call them kind of hard to understand exactly how we might use them, ideas, and apply them to an idea that we may all be familiar with. So I want to just acknowledge the contributor to this, primarily Zheng-Hoon Kong, who's a PhD student working with me, but also Ben Goldsberry and Sam Wallen, who've helped me a lot along the way in some of our work on non-reciprocity. So just really quick in terms of background, I did want to give you all a little bit of an idea where I'm coming from here. I did finish my PhD at Georgia Tech in 2007, quite a while ago, and spent a lot of time actually across the channel from you all over in Eastern France, and did that in parallel double degree program. But then the main reason I bring this up is that I spent about 10 years as a research scientist at the Applied Research Laboratories at University of Texas at Austin. I still maintain an appointment and do a lot of work out there, but I've been a lecturer and research scientist simultaneously at UT Austin Mechanical Engineering Department, teaching and things like that, and then moved to the academic route about 5 years ago. So I also spent some time at GN Resound, which makes audio devices, hearing aids, things like that, which actually plays a lot into some of the transduction type of things that I work with on the side. So as an overview with respect to content here, I'm going to talk about reciprocity, specifically about some of these fundamental principles of reciprocity that we all know quite well and how we might violate that. Then I'm going to talk about sound diffusion, specifically in application to audio applications, and how that might be applicable to metasurfaces, and then applying spatiotemporal modulation in order to violate reciprocity and see what happens with respect to diffusion. And I'm going to provide a little bit of some summary and perspectives on that. So reciprocity, Hussein Nassar likes to say this, this is kind of the oldest version of reciprocity, an eye for an eye. But what do we mean, of course, when we talk about it in terms of acoustics? These ideas were explored long ago, as you may be familiar. Kind of the big names in this group have talked about this for years and years. The one that we tend to think of a lot is Rayleigh's reciprocity, as expressed in sort of any arbitrary medium with point A and B, basically saying that if I have a point source at A or any source at A and I receive at B, that the resulting velocity potential at a second point B is the same both magnitude and phase as it would be at A had B been the source of the sound. So interchange of source and receive in any linear passive medium leads to reciprocal sound transmission in both magnitude and phase. And so I wrote with Romain Fleury and Andrea Liu this paper almost 10 years ago at this point, where we kind of talked about that in broad strokes and sort of how it might be interesting to violate reciprocity. But on a more practical, from a more practical standpoint, it's worth remembering that reciprocity is first of all, it's a very fundamental principle in wave phenomena in general, and we use it a lot, right? We use it in, you should probably be familiar that we use it in a calibration. So one of the best ways to do a real baseline calibration of a microphone or a hydrophone or something or source is actually to use the principle of reciprocity as opposed to a comparison calibration. Matthias Fink in the early 90s showed that you could use, the fact that a medium is reciprocal to apply time reversal mirrors in order to focus through arbitrary media by encompassing any given source with an entire, encircling it with a set of sensors that you could then time reverse the signal in order to focus back wherever the source of the sound was. And we use, and I just like to think, I saw this and I remember, this is the Songa eruption, if you remember, and these are the acoustic waves that were captured by satellite imagery. And, we can use the ideas, we assume reciprocity, although it's not entirely because there's flow and the like, but we can use reciprocity in order to back propagate an infrasound in order to figure out where the source of a sound may be, or using, of course, elastic waves and doing the same. So these things are really, fundamental, very valuable, and we learned how to use them. But then the question is, a reciprocal medium, we tend to use that a lot. It's sort of one of those foundations of acoustic wave propagation. But what if we could somehow violate that, right? So if we could violate that, then we can big picture wise, we can control a lot over just basically wave propagation in general. There's some interesting ideas of vibration isolation systems, sensing vibration without being sensed, these types of things, STAR, which we call simultaneous transmit and receive, being able to transmit from one antenna or one array in one direction while receiving simultaneously in another, eliminating backscattering effects, or at least controlling how that may be. And so, our initial work in this area, we published again in 2014, and we really just sort of capitalized on the effects of flow, basically mean transport, or what we call momentum bias in a standing wave cavity, in order to demonstrate those kinds of principles, which related back to some behavior in electromagnetics, which was very interesting. So, in terms of a little bit of background, I do want to make some disambiguation between non-reciprocity and asymmetry. This is one thing, at least I think, is less confused now as it was in the past. But if you look back on the order of 5 to 10 years, 5 years ago, there was a lot of publications where you'd see things that were actually asymmetric wave phenomena as opposed to non-reciprocal. So let's just consider a slab of material, positive X. We have an incident time harmonic pressure wave, and it can be incident from the left. And we have an incident from the left. Of course, we get transmission. In this case, 1, transmission 1, reflection 1. And then if we're incident from the right, then we get reflection 2 and transmission 2. And so we can represent that as a sort of 2-port scattering matrix, or a scattering representation, where we have the outgoing waves related to the incoming waves via some scattering matrix in this case, where the entries of the scattering matrix are just the reflection coefficient from the left and from the right on the diagonal, and then the transmission coefficients on the off-diagonal terms, so the transmission from left to right and the transmission from right to left. Okay, and so it's important to remember that if the medium is reciprocal, then and lossless and symmetric, then you're going to get that the reflection coefficients are the same on both sides, and the transmission coefficients, of course, are the same on both sides. If it's reciprocal but has some asymmetric kind of behavior, then you could get that the transmission coefficients, of course, will be the same, but the reflection coefficients could be different. And you can get that actually in terms, even in a lossless medium, it'll be a phase difference. In a lossy medium, you can get asymmetric absorption with symmetric transmission. If it's non-reciprocal, on the other hand, but maybe symmetric behavior, you can get reciprocal, the same reflection coefficients and differing transmission coefficients. And then in general, neither of those are useful. So that's, worth sort of keeping in mind. Now, as you get to a more general case, imagine you have a waveguide that could support, let's say, 2 modes. And we've got a mode converter between, mode 1 and mode 2 in those 2 things. And we imagine an incident wave in 1, and then a reflected wave, of course, in mode 1 and mode 2. We have some mode conversion or a partial mode conversion, and then we transmit off into mode 2 and a little bit of mode 1. Okay, and so there was a lot of work a while back of talking about asymmetry, assuming it was asymmetric, because then if I were to, so I have mode 1 in, one would expect, of course, that if I have an incident wave on mode 1 in from the other side, then I would get mode 2. Okay, this is not surprising. It shouldn't be surprising, but there were a fair amount of works in sort of like asymmetric mode transmission, where we played some games with filters, and that could be construed as non-reciprocity. But the thing to remember is that these things are basically the same, right? So you're just literally exchanging, again, source and receive. So in other words, if I have some level of time reversal symmetry of the incoming wave and the outgoing wave, then I get the same mode composition out as I had in, right? So when there are multiple modes present, it's important to remember that you have to have exactly the same modes, everything time reversed, or some condition where you were able to excite with the exact same modes that you received in order to observe your source as it is. So you can play games with like shear longitudinal to shear, shear to longitudinal types of things in elasticity, for example. Okay, so it's reciprocal, but it's asymmetric. Okay, it gets, of course, considerably more involved than that. It's not easily overcome. So if you want to overcome it, then you really need to dig deep. There's a reason why it's so foundational. It doesn't occur trivially. We wrote with a pretty good crew of authors, I guess almost 2 years ago now, a nice review on this. And if you're really interested, there's a lot of information in there and a lot of seminal publications on that are referred to. So I would recommend that you do so. Okay, so how do you break or violate the principle of reciprocity? There's a few ways to do it. So there's active means where we input a mu. Here is a momentum bias, where it's time irreversible. So this was like the case where I showed with the cavity with flow inside, producing an asymmetric mode inside the cavity. Bogdan Popa, Steve Kummer showed that kind of work quite some time ago as well. There's nonlinearity, where you can imagine if you have an incident wave at one frequency, and then you go through a nonlinear medium, then you upshift in frequencies, and then you put that through a linear filter. You can get waves to go back and basically to propagate in one energy to propagate in one direction, but not another, depending on how you order nonlinear media and elastic and filters. And then you can also do work on what we call modulated properties, which is what we're going to talk about a lot today, where we can assume, for example, in a 1D waveguide or a 1D wave propagation, you have that the modulus of elasticity here, the elastic modulus, Young's modulus, and the density could potentially be modulated in some wave-like fashion with some modulating speed that is much less than the propagating wave speed. And that leads to things like the case where here we have our usual band diagram, and we tend to shear the band diagram by the wave number and frequency line, or this particular the slope of the line here would be proportional to the modulation speed of the material, and it would skew one way or the other depending on the direction of the modulation. Okay, so well, like I said, we're going to look at this a bit. We have a few publications on that idea of looking at as sort of mechanical deformations leading to at very slow speeds compared to propagating wave speeds, where you see this non-reciprocal transport. And so let's, that's kind of the baseline there. We're going to assume that if we use spatiotemporal modulation, or what amounts to a propagating prescribed modulation of properties or conditions, we can get non-reciprocal propagation or non-reciprocal effects. Okay, so that's a lot of backdrop, but I think it's important to put that all in context, because now I'm going to make a shift to this idea of an acoustic diffuser, and then I'm going to put the two of them together. Okay, so so let's talk about acoustic diffusers. You all should hopefully be somewhat familiar with those. Acoustic diffusers are the things that you know, there's actually Trevor Cox has done a huge amount of work over the years in this, but diffusers are just in general surface treatments that allow us to reduce the strength of specular reflections, which can be perceived as echoes. They're largely used, of course, in audio, specifically in recording studios, which are smaller spaces, but also kind of to eliminate things like what they call backslap or other kind of, you know, annoying echoes in a performance space. In recording studios, they're often used just to reduce the strength of internal modes, which cause what we call spatial coloring of the room. Coloring in terms of frequency. We have a frequency-dependent spatial distribution of sound. And so, you know, these things have been used a lot, and the idea is really pretty simple. We don't want to necessarily absorb all the sound. We want maybe a live acoustic space. But we don't want those echoes or modes. So the idea here is just that we could produce an irregular surface of sorts in sort of 1D or 2D, and really just take all of the energy that's incident also gets backscattered at you, just with a little bit of a scrambled phase. And so when we do that, you can then sort of disperse the sound. Here's a nice image actually out of Cox and D'Antonio's book, where you have an incident spherical wave. Then you have this what's called the Schroeder diffuser. And then, of course, as it progresses forward in time, you see this, you know, different wavelets, if you want to think of it that way, of outgoing pressure field. This is a Schwerin image. And you can see that the sound gets dispersed both in terms of space and time, which makes the energy more randomized. So you don't get coherence and perception of echoes and other standing wave kind of behaviors. Okay, and so, you know, this diffuse reflection via these Schroeder diffusers is actually really quite, I guess you'd say, simple. It's been known for a long time. And really the way that it's done is you use what amounts to some base unit cell of a grating, okay, a phase grating. So you have something like what's called a QRD, a quadratic residue diffuser, where you prescribe some sort of quasi-random sequence of phase based in this particular case, the original design, as some just difference in depth of different wells. And then we arrange that unit cell, you know, periodically in space, and that gives a quasi-random phase that still has some periodicity to it. Okay, so that is just able to arrange it over large surface areas, and you can get larger order diffusers and things like that as necessary. And so this is relevant to what we do, what I'm going to talk about later. So I want to go through it. The grading equation, and so how do you solve for the acoustic field that gets backscattered off of this diffuser? So the idea here is you have an incident plane wave with some spatially dependent input impedance, or its inverse at the admittance. The grading in and of itself, so in other words, one unit of that diffuser surface has some length, large lambda, capital lambda. And then, you know, we have the incident acoustic wave with some incident amplitude, and then, you know, the projection on the X and Y axes. And now the scattered field will be, you know, depending on frequency, will consist of the specular reflected mode scattered off at 0, and then different diffracted orders at the exact same frequency, plus and minus 1, which will then, and so the total scattered field is the sum of all of those, where we have a different amplitude for each, and a different direction is defined by beta and gamma. Okay, and so those again, now the projection of the wave on the x-axis is just kx, which is the same as the incident wave, plus some integral number of integral multiples based on the size of the diffuser. And then, of course, we just, in order to conserve momentum, basically we have to have that the projection on the y direction or the z direction is just going to be dependent on the background wave number. Okay. And so then that decides which direction everything gets scattered off into. Okay, all right. And so we can do this by using these different well depths, and we can then define the depths based on how we define our input admittance here in this particular case. This is a normalized admittance, which is just based on the depth and the wave number in the material in the background for 1 or 2D. Okay. And then that's just going to be dictated by, this depth is dictated by the wavelength of interest. So we did a little bit of work that I'm going to show you just for perspective, where we said, all right, well, it's fine and good, but these end up being a little bit big, right? Sometimes if you want to get to low frequencies. So can we shrink that down? And so we started looking at acoustic metasurfaces to do this, all right? And like I said, I'm going to bring this all right back into non-reciprocity and show the motivation for why we might use non-reciprocity. And so a metasurface is basically what amounts to an acoustically thin surface that generates, quote unquote, arbitrary control of reflected and transmitted phase, or also, absorption. So this permits the control of this. And when I say acoustically thin, I just mean much smaller than a wavelength, or at least smaller than we can get usually. And the idea here is that we can impart, if we have half space 1 and 2 with different material properties, they could be the same, but they could also be different, that I can prescribe some arbitrary phase function along the x-axis. And when I do that, I get this generalized Snell's law, which you all may be familiar with. But basically, it says that we don't get the usual case where the reflected and transmitted directions are the same. They depend on the gradient of the phase function at the metasurface. You want to call it a phase screen if you want. And so when we solve these simultaneously, we can get control over both the reflected and transmitted amplitude. And if you include losses in the surface, you can also control the absorption dependent on direction and things like that. And so there's been, a lot of work of this going back to 2016, a group in China, Bin Liang's group, and then Noé Jiménez, who you all probably know, did some interesting work by looking at a sort of standard sound diffuser and a metasurface sound diffuser, showing that you get comparable behavior. In this particular case, it was like lambda over 20 as opposed to lambda over 2, but it was more narrow band because it's a resonant type of phenomena. Same sort of thing with what Noé did a while back. Theirs was also a little bit more broadband than this. It was also arguably more tunable because of that. You could keep it in a smaller form factor. So we were interested in doing this and kind of in a more, let's say, without using resonators, we looked at it for these coiled space surfaces, right? And these are basically, we looked at these surfaces where we took inspiration from Guancolo Mamoli's work, where he's looking at it for using it for transmission of acoustic waves to manipulate particles and the like. And there are these coiled space structures that basically add phase by making the pathway more tortuous, but what they used was more open, so there was less loss. So we looked at creating a sound diffuser in that way, with sort of these baseline ideas where we wanted to match the phase based on the diffuser design. And we instead used the coiled space structure where we wanted to look at it being a lot smaller, okay, or thinner. And so we did a lot of different designs where we looked at different shapes, of course, nice, simple parametric sweeps and effectively through finite elements where we wanted to match the reflected phase over at a specific set of frequencies using this metasurface design, and specifically where we had minimal losses, right? And so the main reason that I bring this up is that we, were able to then turn around and replicate, a QRD in 2D, where we have 4 periods of those. And then the equivalent one of 4 periods in the AMS diffuser, which is effectively 4 times thinner. So thinner, not 20, but 4 times. And we then took and built all these with just some additive manufactured parts. You'll notice that they're actually scrambled in orientation in order to eliminate some bias that occurs because of the shape of that tortuous surface does influence a little bit the backscattered field. Okay, and then we took an acoustic, excitation in an anechoic chamber. Then we scanned out some trajectory. We did some interesting work in impulse extraction and subtracting the scattered field off of the gantry system, and we're able to measure this dispersed sound in space and time. Okay, so we had an incident, not quite plane wave, definitely not plane wave, but some spherical type of wave. Okay, and then when we did that, we were able to compare the AMS response and the QRD response. And visually, you can tell here, this is the backscattered energy as a function of basically the polar angle and through all azimuth. And you can see that you get quite wide diffusion. And if you look at the diffusion coefficient, you can get the same behavior with about a λ/4 thickness. λ/8 thickness as the design of the QRD, which gives us some arbitrary control over that with a much thinner surface, which becomes potentially more practical. Okay, so that's a diffuser, kind of standard type of stuff, nothing super exciting with respect to, definitely not with respect to non-reciprocity. So why did I go through all that detail? Well, there's a reason, is that there's a problem with the sound diffusers. You're limited into how diffuse you can create the sound field if you rely on a purely passive, or I guess standard reciprocal medium or standard reciprocal interface. And so we wanted to overcome that. Okay, so this classic diffuser design, of course, there's limitations because those individual, if you want to call them unit cells of your quasi-random scattering surface, is still arranged periodically. And even if you arrange that quasi-periodically, you still run into problems because you just, spatially, it's best to arrange it periodically. And so you either get worse coverage or you just, you still end up with these grading lobes. And these grading lobes in the backscattered field, so you get, of course, nice, incident at plane and then scattered off in a lot of different directions. But you're still not going to have this idealized diffuse scattering, which is to say, incident plane wave at basically what amounts to a single wave number, and then equal energy scattered off in all directions, right? That's really what you want to do. You want to do that, take it off in all directions, and then also scattered in space, or sorry, in time. And so those nulls are problematic a little bit. And so we're looking at the literature and some non-reciprocal, work in optics. And there is these interesting papers on this idea of taking a metasurface, in this case, an optical or electromagnetic metasurface, where they had engineered, of course, the surface input impedance. And they said, I can design, in a reciprocal case, I can design an incident wave to go off in whatever direction I would like. But if I modulate that input impedance or input admittance, I can get it so that it scatters off at a shifted frequency. And even if I come back at that same frequency, I get even a different frequency back at a different direction that I had incident. So, just kind of showing in a general sense, this is, by the way, this is wave number space, kx, ky. And these are the equifrequency contours of direction of propagation. And then they took that same idea just last year, I guess this was published, where they said, all right, well, we could also potentially modulate the surface, in this case, the input dielectric permittivity, and we modulate that, and we could actually take waves incident from different directions, potentially even incoherently, and get them to all scatter off, the power to scatter off all in one direction, just by engineering not only the distribution, but also the modulation function. Okay, so could we use that then potentially to improve, if we could say, take energy and put it off to go in one particular direction, could we actually make it so that we can make it go off in all directions equally, or at least make it more diffuse? And there's a couple things to keep in mind here. Can we diffuse it in both what amounts to in space, right, as I showed before, energy going off in all directions, but also extend in time that signal. That's part of what's happening. These two things are kind of two sides of the same coin. And so the idea here is, if you have, as an example, a simple 1D diffuser, and you can have your original arrangement, if you want, of your spatial distribution of the input admittance, and then you add in some modulation function. In this case, we're just going to look entirely at first just at some single wave, just single frequency modulation omega m and wave number km. So we have the original distribution, and then we're going to add some modulation that which can modulate in one direction or the other. Okay. All right. So then how does that? Oh, I'm stuck. Let's see here. There we go. All right. So if we do that, so how does this change our little grading equation that we were looking at before? We have an incident wave, of course, a function of time. And now we're going to assume that our input impedance or admittance actually is a function of not only space, but also time. Okay. So that could be just the case we had before, where maybe you just literally change it as a function of time uniformly, or you can change it in some modulation function where it propagates along, propagates whatever, it's modulated in some deterministic way. So you have the same incident wave, of course, right? But now I've kind of explicitly called out that we have the incident wave frequency. And now, in order to be more general, we're going to have to consider the fact that not only do we have the backscattered wave for every order of our diffraction field, but also that diffracted field will be also at the frequency of interest, right? The frequency of the incident wave, and upshifted and downshifted as well, potentially, by the modulation frequencies. So every single diffracted order will also have energy scattered off at slightly different frequencies, which are integer multiples of the frequencies of the wave number, or of the modulation frequency. And so how do we deal with that? I'm going to kind of talk through the analytical model of that. I'm going to show a finite element validation of that idea. And I'm going to talk a little bit about how that will be implemented experimentally, which we're doing right now. And so the main point here is that the scattered wave is now going to be still some summation of all the different diffracted orders, but those diffracted orders are also going to have, for any given diffracted order, it's going to change as a function of time because I'm modulating the surface. So every single diffracted order term will have some modulated, some functional time, some time dependence in and of itself. So now our projections on the X and the Z axes depend on, kind of the usual projections based on the periodicity of the grading. But now we also have that the wave number in the background medium is going to be a function, the wave number in the direction of the backscattered field will depend on, sorry, let me just say this, case of P, where P is the modulation harmonic count, okay, so number. All right, so the main point here is that because it could happen at frequency omega I or omega I plus omega P times omega M, then I'm going to have different wave numbers depending on which component, if you want, which harmonic we're looking at. Okay, so then how do I handle that? Well, let's look at the scattered field. We know it's a summation of all of the backscattered orders, which depends on both the diffraction orders as well as the modulation harmonics. So we can express those modulation as the amplitudes as a Fourier series. Okay, so if we sum that as a Fourier series, then we can just assume that for every diffracted order, there's also a modulation harmonic, and that those depend on the omega naught, which is the incident energy, plus P times omega M, which is the modulation frequency in and of itself. Okay, so then what we want to be able to do in order to figure out what our backscattered field is we're going to get our modal amplitude for the nth diffraction order and the P modulation harmonic, and that's going to then dictate the direction at which energy is backscattered at for every single one of those combinations. Okay. All right, so let's now figure out how we can determine what the backscattered field will be, and in order to do that, we need to define the modulated surface as some functional form that I can get in order to just get at the problem in order to solve it. So in order to do that, we're actually going to take and expand the surface input admittance. This is, in this case, it's normalized by the background impedance, right? So the admittances are reciprocals of each other, the admittance of reciprocals of the impedance. So we're going to say, all right, well, let's just write that as some expansion where we can define a modulation function chi of P also as a Fourier series. Okay. And so this is, it doesn't, it's if P is equal to 0, then we just have there's no modulation. We just have the original distribution, which is given here. Okay, so there's our original distribution if we're looking specifically at this diffuser, sort of classical diffuser design. And then what we want to do is augment that by saying that those could also be modulated as a function of time and space. And we'll talk about how that can be done in a little bit. Okay, so then how do we get the model? And I'm really just talking through this whole in detail in terms of how do we model the behavior. So the temporal modulation really just means that the normal velocity function now is actually going to depend on that modulation frequency and at every single point in space. So conservation of momentum tells us that the normal component of the velocity field is just going to be given by this usual ratio, which is the input admittance at that point in time and the total surface pressure at that surface. But now we got to be careful because our total surface pressure is going to depend on the incident pressure, of course, as well as the scattered pressure, which is this double sum on modulation harmonics and diffracted orders. Okay, so it's a little messy, but it's deterministic, right? We can write it at least. And then we also know the input admittance can be expressed in the same Fourier series form, which is helpful. That's what allows us to get our equations that we need to get. So, this is a big mess, but we can then, of course, take that expression, we can input that in for the conservation of momentum equation, okay, and then solve for the backscattered acoustic energy. Okay, so in order to do that, we clearly, practically speaking, we don't want to include all amplitudes. So there's a lot of things that happen turning the crank to get this working, but, basically we're going to assume some modulation amplitude and frequency. We can sweep through those things and do a little bit of discovery in doing that. We use, in the process, you have to use orthogonality. This gives us, whatever, it makes everything nice and clean. And then we're going to truncate at diffracted orders and diffraction modes and modulation harmonics in order to have a finite, to capture everything. And basically the way we do that is we assume a certain set of modes and harmonics, and then once we do that, then we check and we increase a little bit, and it kind of like a convergence, like mesh refinement study kind of idea, but with respect to just making sure you have everything, all of your energy accounted for. So we take all that, we substitute that in there, and we end up with this really messy block matrix formulation. And I'm not going to explain all the details because it would take definitely the rest of the time that we have, which is not a lot. But here what you have is you have basically block vectors for every single, so here for every modulation harmonic, okay, P, you've got 2n diffracted orders, right? And then here's your incident wave, of course, which is, you end up with this extra mess because of the modulation, but these are all input values which you determine based on the assumed modulation amplitude and frequency. Okay, and so what that means is that so every single one, you're going to invert this big messy matrix for all of the modulation amplitudes for every modulation harmonic in every diffracted order, and that's going to give you basically some set of unknowns of modal amplitudes is 2n plus 1 times 2p plus 1 terms. Okay, and then that's going to determine our entire sound field. So just as an example to show how this works, we're rounding it up here. If I have initial, I'm going to assume a baseline of n equals 7 QRD design. Just assume a design frequency of 5 kilohertz, just because that's a nice audio band. And we're going to be on the order of, 0.12 meters for our unit. And then this is basically the admittance phase distribution that you would see. Okay. And then what we want to do is we want to add in this modulation frequency. And I've got just a quick little animation here. So we're going to modulate it, point-wise, just up and down. These are numbers of susceptance or admittances, which are realizable, we think, based on what I'll talk about at the very end. And so what that means is if I look at 2 periods of the diffuser, that if the red is the initial distribution of the scattered, the input admittance, then this is what it would look like, the admittance would look like. And it's not literally moving, it's just the admittance is changing as a function of time and space. Okay. All right. So then we do that, and then we're going to basically run through our semi-analytical model and see what happens. Okay. So incident wave, and I shouldn't say we're just going to see what happens. We run a bunch of models and find something that's useful, and then we talk about that, right? Okay. So this is a really interesting way to look at this. So this is our scattering amplitudes for, again, diffracted orders, okay, and modulation harmonics. So we had 30 diffracted modes we considered, 20 harmonics. And this is basically the energy or the amplitude, okay, for the case where there's no modulation. So there's no harmonics, we're at 0. And then incident wave comes in, and then energy gets shot off on each direction. Those are diffracted modes, right? And so this is what gives you your grading lobes, right? There's only energy at those particular modes. And now if I introduce a modulation in one direction or the other, I'll show both. What you see is that now the energy is, first of all, scattered in, here's your incident wave frequency. And this is for different frequencies. So there are additional modulation harmonics. And then also it's scattered off each of the harmonics even is scattered off in each diffracted, they have their own diffracted orders. So what you can see, just literally, this is time, sorry, and this is space. And so you can see that what was already initially, spread out in space is now spread out in space and time more efficiently. Okay, now not all of these propagate. I forgot to overlay which ones propagate, but basically there's a few evanescent type of modes. And you can see that as you flip the modulation direction, it kind of flips this symmetrically. But the main point is it's not, there's a lot of energy scattered off in a lot of directions. We did check, by the way, and it's all energy is conserved here. We're not introducing energy. Okay. All right. And this is just to see it. This is a polar plot. So the dashed red line is the case where there's no modulation. And then this is just the propagating modes scattered off. And you can see they're kind of, each individual one is diffracted. Its energy scattered off in all directions. Now, this is the case of this is the scattered field, red, with no modulation, okay? And we're gonna say at every single frequency for an incident F0, we're gonna take all of the diffracted energy and we're gonna sum it all together in every given direction. So it will include frequencies that are not at the incident frequency, which raises its own question if you're talking about audio, but we'll just leave that there for the moment. And what you can see is if you modulate it in the backward direction, in other words, negative X, or positive direction, forward direction, you can see that basically this is the total energy, or basically the backscattered energy. You can see there's still, of course, some uneven distribution, but it's more diffuse than the original case by quite a bit. So here is a finite element model, which is a time domain model by definition, must be. And you can see that it's similar. There was certain assumptions we had to make based on the finiteness of the sample and getting the COMSOL to work. But you can see from big picture wise, of course, the unmodulated case looks very similar. The nulls are in basically the same direction, and you can see also the diffusivity is basically kind of this mirrored behavior, but it's much more diffuse, which is really quite interesting. I'll talk about that in a little bit because it's helpful and informative actually to look at the finite element simulation because we can see the entire field. I can do that with the analytics too, but it just takes a lot more work. So, okay, so let's look at this. So on the left-hand side, I've got the non-modulated. Here's a QRD surface. I just have a block here, but this is basically your uneven sort of your quasi-random phase distribution here. And then on the right-hand side, I have the quasi-random phase with the surface modulation. Now, again, it's not literally moving. We're just assuming the input impedance is modulated as a function of space and time. Okay, incident plane wave normal. And then you're going to look at the result you're going to see is it's a time domain simulation and it's just the scattered field. So it's going to look like it's emanating from there, but I've just removed the incident field. So you're not seeing the total field, you're just seeing the scattered field for clarity. Okay, so here's the unmodulated, here's the modulated. And what you can see is, so the unmodulated, you can see you clearly get your lobes, your main lobes as you would expect. And with the modulation, what you see is that there's no, there is a little bit of, there's more energy. There's still kind of like those original modes, but you can see everything is just more mixed in time, right? So you don't get some coherent summation off in any given direction because actually what's happening is the amplitudes of each of the things, and the amplitudes phase at every single point is changing as a function of both space and time. Which is really quite intriguing because now you've got the same surface area but you're able to get significantly more diffuse energy from a single frequency incident wave. Okay, now, so we can quantify this. There's something known as the diffusion coefficient, which is just, it's an autocorrelation of spatial similarity, classical architectural acoustics kind of measurement. You can look it up. It's not terribly complicated. It has to do with the sound power levels in any given direction. And so basically, the bigger this value is, the more diffuse the sound field is. So we looked at this case and we ran it for the same modulation frequency and amplitude as a function of different incident wave energies, or incident wave frequencies, I apologize. And then if we have, the bigger this is, the closer to 1 would be a purely diffuse field. And so if you get down to it, the unmodulated one shows tremendous difference. There's, pretty good behavior already. They already do a good job. But you bump these up by, 0.1, 0.2 is actually a very notable difference in diffusion coefficient. Now, this is broadband, assuming you can make something that can modulate broadband. And that's, potentially the real catch, maybe. But we will see. So, now, so here's the idea. So that's saying this really could work quite well, right? We can get a much better diffuse field from the usual kind of classical diffuser surface. All we have to be able to do is to modulate that surface as a function of time and space, which now that's okay, if we could do that, right? That's always the hard part with metamaterials. So the next step is the realization of this. I was really, really hoping that I could show this. I thought we've got it sort of working in our chamber right now. But we've made this QRD sample. We had to learn a whole lot about single board computers and talking to, all these sorts of things. And it's been fun, but it's been interesting. So our next step, we're gonna create a sample. And we're going to use this little piezoelectric disc termination. Okay, so we're not going to shrink it together like our little AMS, but we're going to use the usual depth, okay, for our diffuser design. And then these are little shunted piezoelectric bender elements, okay. And what we can then do is we can use what's known as a negative capacitance shunting circuit. So we can drive that capacitance from larger to smaller values. And each of those individual wells then can be modulated independently on their own. So we take our computer, we communicate via a single board computer to what's called a digital potentiometer, or in order to change basically this resistance. So we can change a ratio of certain resistances as a function of time for an individual one. And then we phase them on a multi-channel output in order to do what we want to do, okay? So that's the next step. And we've verified that we can do that in the impedance tube. And we're basically right now just in the middle of making a multi-channel controller, because buying a multi-channel controller costs $50,000. So we're just making our computer do it. So we're just being electrical engineers while we figure out how to do this. So, okay, so that's the next step. What I can say that's really important is, first of all, doing this does not introduce audible noise. So I am changing the electrical impedance, which in turn, because it's a transducer, changes the mechanical input impedance. So we literally, this was my biggest concern. It was one of the first things we did. Now it might be, maybe it's not really perceptible, or, but we measured it in our impedance tube. It sounds fine, meaning we don't hear anything. We see some electrical noise, but not any mechanical noise or audible acoustic noise. So it is literally just changing the input impedance. And it's doing so via this shunting thing, which basically is a very high input impedance op-amp circuit. So it's like changing the impedance on a microphone preamplifier board, if you are familiar. Okay, so that's good. Now, there's some questions about what that might do to audio quality, and I'll talk about that a little bit. I'm sure people will have questions on that. But big picture wise, in summary and outlook, acoustic reciprocity, we can break it using violate that principle via spatiotemporal modulation of properties or admittances. Okay, so that's this surface admittance. We took that path a little bit because it seems like potentially a more practical way to get at the problem, at least initially, to some practical implementation. So this enables some really new concepts in acoustic wave control, presents potentially some really significant scientific and technical challenges. So changing properties in time and space is one of the, I would argue, is one of the really interesting and very difficult problems that's out there for this community, I think. How would you actually do that? 2D surfaces, things like that are probably reasonable. 2D materials, not graphene, but 2D plates and those kinds of things are potentially easier than others. And then we went and showed that sound diffuser performance can be improved by modulating a surface admittance. By controlling the modulation frequency and amplitude, we can control where energy is scattered into various modulation harmonics and directions. We derived this analytical finite element predictions, and they're in agreement to derive the finite element, or the analytical model validated with finite elements. And the experimental demonstration is in process and is hopefully imminent here. There's some implications for perception, which I'm happy to discuss about this if we use it for audio. I think some of that's going to be, should we just do it and see what happens? But then in general, this is really interesting because it drives, partnerships between material science, systems design, acousticians, mechanicians, in order to do this modulating in acoustic and elastic media. So that's all I have for you all. Open for questions, and I wanted to thank our funding sources, which helped with this in various pieces and parts.
Okay, thank you very much. I'll do the clapping on everyone's behalf.
Okay, thanks.
So if anyone would like to ask a question, please do drop that in the chat, and I'll get to those. You already alluded to one question, so I think I'll ask that whilst we wait for all the questions to flood in. And I was wondering how big a frequency shifts you can achieve. So I have to apologise. The RAF are flying over the top of my house at the moment.
Oh, that's what I can't hear them. So I think.
Yeah, A400, 4 props. I'm surprised. Yeah, what's the maximum frequency shift, and have you got further thoughts on what the implications are for diffusing audio sound?
So the one thing that we've looked at, there's a few things that are really quite interesting. And I'm now realizing I meant to put this in here, I forgot. So if you look at, you can think of the parameter space of this as the modulation frequency and amplitude. And there are different regimes of this. And actually, if you look at our review paper, you can actually see some of this, where when you look at a modulation amplitude that's relatively small, okay, but the frequencies are low, then it's like modulating the properties, right? It's like it's akin to your sub-wavelength approximation when you're talking about metamaterials or composites or something like that. Okay, so depending on which regime you want to remain in, you would like your modulation frequencies to be, 1/10 or at most 1/5 of your frequency of operation. So with this example, we designed it at 500 kilohertz, or sorry, 5 kilohertz, and we modulated at 500 hertz. So we were about 10 down. And that a factor of 10 down. So that was helpful, or that keeps things where now your backscattered energy is at 5 kilohertz plus or minus, increments of 500. So you have a few harmonics, and you are changing it a fair amount, right? So as you bump up the modulation frequency, then you're going to change the distribution of frequencies that get backscattered at you. Once you modulate really, really fast, there's this weird thing. It's like a flicker fusion, right? Where if you modulate really, really fast, then it's almost like having it uniform in time. So as far as the acoustic wave is concerned. And so there's these regimes that you see if you plot those, like the total backscattered field, for example, at a given direction. You'll see that it will go through these regimes where you'll get really strong diffusion and then you get really weak diffusion and like beaming, kind of like they showed in the optical case. And that's actually something we're trying to understand a little better right now. Okay, and one real quick, I'll answer your question about audio. So I'm not real sure what this is going to do, because the backscattered field will have those, you can think of it as a contaminating frequency in the sense that, or contaminating audio, because you're getting energy back at frequencies that you didn't input. Okay, but if it's just to sort of diffuse and reduce echoes, it might be better. I don't know. there are classical architectural acoustics types of metrics for these kinds of things, which we're going to apply when we get the system out to sort of see what that does. And we'll probably have people listen to it, although we can't put it in a whole room right now. So I don't know.
I think, like, unless you've been in a lab where it's playing single 5 kilohertz tone, you don't realize how annoying that is. And having it diffused and having it smeared out in frequency as well might actually make it more palatable.
Right. And then if you put in a multi-frequency signal, remember there's a lot happening at every single frequency. You're getting modulation harmonics. So like you're having energy in all the different, it's backscattered in all the frequencies for plus. So
yeah. Okay. So there's a couple of questions in the chat.
Yeah.
I can read them out if you can't see them. So the first question is, what is the bandwidth of the design? Or what bandwidth can the design achieve? And I suppose there's a number of metrics you can choose for what the
right. So that comes down to the practical implementation a little bit. So right now, we're seeing the most efficient, we can get the most modulation amplitude by using almost kind of like a lot of metamaterials, where if we shift a resonance of a termination around. Okay, so then that's dictated by the termination resonance. In principle, and again, it's principle, if you can design a circuit for a termination that happens independent of frequencies or whatever broadband, whatever bandwidth you can modulate the impedance, then it's never infinite bandwidth, but you get the idea, right? So it's very dependent on what that specific termination is, like how you implement it.
Yeah, almost what your initial impedance profile.
I think, yeah, exactly.
Okay, so maybe we'll call this a final question given the time.
Yeah.
So the question is, for this kind of surface that stretches an impulse-like signal across time, can you choose a time-reversed incident signal to use this diffuser to focus a signal in time? Or is this broken because of the reciprocity?
So this is a really good question. I've actually, it was funny, I thought of it a while ago, and then I was looking at the slides with the time reversal symmetry, or the time reversal mirrors that Pinkscrew did. I'm not sure. So I think you probably can, you've broken time reversal symmetry, but you've done it in a deterministic way, right? So the work in the optics group that I showed, they showed that you can concentrate energy in a given direction for waves coming in at various other directions that are incoherent, which is interesting. So I think my short answer is I'm not sure, and I think you'd have to do an inverse design of sorts. It's not clear to me that there's a clear functional representation that would tell you yes or no, right? It's hard to, yeah. So it's not the best answer, but I think so. I think you could, but I really don't know. You'd have to design your modulation function is the main point.
Yeah, okay, very cool. All right, so yeah, let me thank you again. It was a really interesting talk. And yeah, we learned tons. So yeah, thank you very much.
Yeah, okay, well, thank you very much. It was good. Thanks everybody for coming. It was a pleasure.
I'll hang around for a second. Just yeah.